Okay, go ahead. I'll give you a sign at 5 minutes. Please go ahead.
Hello, everyone. My name is Korsakova. I'm a postdoc at CERT at Paris Observatory, which is actually very close here. And I'm going to talk about gravitational waves, and in particular gravitational waves with LISA, and the ways to do the fast parameter estimation with normalizing flows. This would be a bit similar to one of the overview talks that we had before, which introduced normalizing flows, but that would be a kind of application of these techniques in our field. But first I want to just introduce what is LISA and what problems do we have. So LISA is a laser interferometer space antenna. That is a gravitational wave detector that is going to be that is going to be like 3 spacecraft separated by 2.5 million kilometers, following the Earth on its orbit, and it will detect gravitational waves in a lower frequency band compared to the ground-based detectors. So for the timeline, I just wanted to mention that at the moment we are in the... can I?
Just have to be calm with it.
You have to be calm, maybe on this side. If you go on.
There it is, there it is.
So at the moment we are here at the mission adoption, which is happening right now, and we plan to launch it at 2034. So these are the sources that we are going to observe with LISA. They would be signals such as massive black hole binaries, galactic binaries, extreme acceleration spirals, and I'm going to talk about massive black hole binaries now. Massive black hole binaries are the signals when, for example, the supermassive black holes that are located in their centers of most galaxies collide with each other. And there are different predictions for how many signals we are going to see depending on the scenario of their evolution. So there are either light seed scenario or the heavy seed scenario, and that would influence the masses of the signals that we are going to observe, their lengths in our band, and also how many sources we would see. So we expect that we are going to see from 10 to 100 sources per year. So why do we need to do machine learning for this kind of data analysis? And the main motivation is that we want to do very fast parameter estimation, because we expect that for massive black hole binaries we actually might observe the electromagnetic counterparts, and some studies say that we would see the counterpart during the merger, and some studies say that we might even see it during the in-spiral phase. So it is very important to perform parameter estimation in like minutes. So yes. Now I'm going to introduce the method that we use. So just wanted to start with the usual bias theorem that we use for inference always, and the main problem, as we all know, in the bias theorem is that we need somehow to compute the marginal likelihood for the observation, and it is not possible to solve this in the exact way, but there are different simplifications, and so you can either do approximate inference by doing some sort of sampling, MC or nested sampling. This is what usually is done at the moment in gravitational waves, or you can use invertible flows or normalizing flows, and that's what I will talk about. So the basic idea of the invertible transform is that we have a simple to sample distribution, like a normal distribution, and we want to be able to learn the map, how we can map from the simple to sample distribution to the complicated distribution, which would be our posterior. So we define some sort of bijective transformation, and then we learn this bijective transformation. This is a very simple idea in general. For example, in the case, if you have just a one-dimensional case, it's very easy to see that you can just preserve the volume of the probability and then transform from one variable to the other. You can just get this concept from the equation of the change of variable equation, which you can write from the definition of probability density function as the derivative of the cumulative distribution function. So for the multidimensional case, that would be simply the distribution that you're interested in is the simple to sample distribution, which is transformed with a determinant with the absolute value of the determinant of the Jacobian. Let's look more carefully at this equation and let's see how practically we can implement this equation. So if we write the log of the change of variable equation, we see that we need to take care of several parts. So first, the transformation that we define has to be a bijection. Then the transformation and its invert has to be differentiable, and also the Jacobian determinant has to be tractably inverted. Another problem is that the calculation of the determinant of Jacobian is a computationally complicated problem. So we have to find a way how we can make it faster. So one of the way would be to make it small or to make it diagonal. Or for example, if you have a triangular matrix, the determinant would be just a product of the elements on the diagonal. And so if we take all these components into constructing our flow, then we can make a computationally easily calculatable flow. So let's look at an example of such flows. For example, if we make a affine transformation, which means that we do the scaling and shifting, we see that the log Jacobian of such transformation is just the sum of the scale values. And the other important aspect that we have to take into account in the construction of the transformation is that how do we deal with the data that has multiple dimensions. So one of the ways to tackle this problem is to use coupling transformation. This is the transformation in which you separate your data into two subparts, and then you transform one part conditional on the other part, and then you do it iteratively, therefore preserving kind of correlation between the parameters. So, for example, in one of the first transformations that were proposed is called real non-volume preserving flows, and here is the expressions that are used for the coupling transformation, and here is the expression for the Jacobian that they have. And in this transformation, you see that there are some functions S and T, and these functions can be just parameterized with any neural network. So it can be fully connected to residual network or any network that you think works best for you. In addition to that, to preserve, to be able to learn complicated distributions, you might want to make several transforms in a row. This is where the name flow comes from, so you make this transform iteratively. So the flow that we used is called spline neural flow. In this flow, they replace affine transformation with some sort of piecewise function. For example, the one that they used was rational quadratic splines. Now, for the optimization, you optimize your flow just by maximizing the total log likelihood of the data. The problem for us is that you need to condition your flow on the data, so because you don't have access to the samples from the posterior distribution. So instead of having access to samples from posterior distribution, you say that you have access to the joint sample. So you have a prior, and then you can simulate your data knowing your waveform and knowing the realization of your noise. Another problem that rises there is that the waveforms are very long. So, for example, the data for LISM, the waveforms might last years or a couple of months. So we need to find a way how we can embed the waveforms. And the way we try to do it is using the singular value decomposition. So the basic idea is that you just find another basis in your data on which you can project it similar. So it's like PCA, and then you just remove all the components in the data that doesn't have high variance, yeah, that's how we project our data on the reduced basis. And these are the results. So they compare quite good to the results from the sampling, but we are still in the process of making them to match exactly.
I was all ready to use the bell and everything, so thank you very much. Do we have some questions or comments from the audience? Karim.
Thank you, Karim Abed. Can you go back to your result in the end? You were pretty quick on them. So I see multiple peaks. Is that something which is expected, or?
Yeah, that's actually very important. So it's a sky localization, and it has a multimodality. And some samplers don't find multimodality, and it's important that this method actually sees it.
So here, in this case, you reproduce correctly the multimodality that you expect.
Yeah. We expect that it should be there.
Yeah, it's nice.
Do you have some more questions? Hubert.
Thank you for the talk. Can you go back and explain a bit more how you condition your flow?
So in the way they usually use this in machine learning is that they assume that they have samples from the distribution that they want to learn the map to, but we don't have access to these samples. So instead we can generate samples from the prior, but then for each sample from the prior we can generate an artificial data. So we generate the waveform for the set of parameters, and then we generate some realization of the noise. And then what we do basically is we combine the values of the parameters plus this conditioning, and we transform all of this vector. And because the data is really large, we need somehow to compress it, and so we compress it with SVD plus some other networks on top of it.
Thank you.
Thanks very much. More questions? Okay, well thank you again. The next speaker, please come down.